I'd like to thank Professor Vanessa Petrosian for his kind invitation and to you all for lending me your time and attention. This is a joint work with a couple of my colleagues.
Professor. I'm not professor, sir.
Okay, to my dear old friend, Dr. Vanessa Petrosian. This is a joint work with a couple of my colleagues from Veracruz and from Sonora, respectively. I'll be talking about controlled Markovian diffusion with multiple modes and imperfect information. We will model the imperfection by including a second agent, which we will call nature. Hence, we'll deal with a game against nature. Okay, I work at the only faculty of actuarial sciences as such in all of Latin America at Universidad Anáhuac, Mexico. This is an overview of the talk. We'll focus on a couple of numeric examples and use them to introduce sufficient conditions to ensure the existence of the optimal average payoff and an optimal strategy for the main controller on an infinite horizon. In general, switching diffusion looks like this. You see? Now, this parameter right here stands for a continuous time Markov process with a finite state space. This one here. Now, this is what in the literature is called a switching diffusion. As I said before, we consider a control system on an infinite horizon with imperfect information. We model the situation by including a second controller here. This is what we call a game against nature or robust control model. For our first example, we consider an extension of Tahbonen and Kawaguchi's model for controlling the accumulation of pollution by waste in the water, in the air, and in the soil. Oops. Okay. Now, our dynamics given by this control diffusion right here, where X stands for the current pollution stock in the environment. Now, observe that despite there is no explicit dependence on the continuous time Markov chain theta, we assume that the main agent's decisions are based on its existence. Because if we are in the bad state, then we can produce just up to eta. But if we are in the good state, then we can produce from eta to gamma. Such Markov chain works as a pendulum, which can be handled by the government, whose decisions cannot be anticipated, but must be followed. In this model, nature will be represented by this parameter right here. Here, alpha represents the rate at which the environment cleans itself. This diagram represents the probability of transition of the continuous time Markov chain. Note that should lambda equal mu, then we have the simple random telegraphic signal process. The idea behind this Markov chain is to work as a traffic light. When the light turns red, there is a lower limit of consumption, say theta, than when it's on green. Then it's on mu. Ideally, this should depend on the actual pollution stock. However, we assume it to be independent. Yeah, please.
I missed something, sorry. The decision of the threshold for switching from good to bad or bad to good is a strategic variable of or not?
No, it's not. Actually, it depends on a third party. It could be the government, right? Okay. So that's, we have the central agent, we have nature, and we have a third party, which could be the government, who controls the pendulum or light, traffic light.
Okay. Mm-hmm.
Okay.
So for exogenously fixed government strategy, you are going to compute the behavior. and then you can vary the government policy to see what's best. Is that the idea?
Yes, precisely.
Okay.
Great, thanks. Now, ideally, this should depend on the actual pollution stock, right? Precisely the question that the professor just asked. However, we assume it to be independent because it might depend on an action of yet another party. In the example I just gave, it was the government that affects the decisions of the central controller and thus the evolution of the. Now, in this numeric example, you see, mu is greater than lambda, right? Probability of having, here we can see the probability of having a green light, of having a red light. Now, we use this to simulate 3 scenarios for the trajectories when the pollution stock will, the pollution stock will take. In the first, nature acts benevolently. That is, it just cleans everything, right? Now, in the second, nature acts as random, and it just cleans a random amount of pollution. But in the third, anything. Now, we cannot just see it in this column here, but I assume that the lower limit of what nature does here is equal to 0.01. For all these simulations, we assume that the central controller consumes as much as the official restriction allow. That is, U should be equal to eta in the bad state and to gamma in the good state. These are some of the resulting trajectories under these scenarios. So here is the resulting trajectory, our resulting trajectory when nature, this one stands for when nature acts at random, but this one stands for when nature acts malevolently. Now, the reward function for a performance index is composed by a social utility for consuming and a social disutility for the pollution stock, this one here. Observe that there is an explicit dependence on the state of the pendulum or traffic light here. You see? Here and here. Now, the performance index will fix for the central controller is this long run expected average of the rewards when t goes to infinity. Now, to implement a simulation with the tools we readily presented, we compute one realization of the ethos integral, you see? So here what we do is that we just use Euler-Maruyama's method and compute one integral. And then we use the Monte Carlo's algorithm. Now, here are the results of our implementation. For one integral and for the average of all those integrals, when the nature acts benevolently, when the nature acts at random, just one simulation in this row, and when nature acts malevolently. But in here we have an average. And I am cheating a little bit because I am fixing the controllers at these levels, 1 and 2. Recall that we are assuming that the central controllers consumes as much as possible in all 3 scenarios. Now, I like to believe that the former part of this presentation will appeal to novel users of our tools. However, for those of you who are more acquainted with these materials, all of that may result a bit trivial, if not just plainly boring. Here, I present what in all our papers we call standard dynamic programming tools. So we use the infinitesimal generator of, in this case, switching diffusion to state these Hamilton-Jacobi-Bellman equations. Now, this is the central result of our talk. The details can be consulted in the link I am sharing with you right now. Oops. Here in the chat. There. So first, we assume that the system, and in this case it was something of some Basicek-like form, meets some ethos conditions, that is Lipschitz and linear growth, right? Second, we assume that the system is Lyapunov stable, and moreover, it is exponentially ergodic. I'll delve more deeply into this condition in the next slide. Now, the consequence is that the scalar J in the Bellman equations we just saw coincides with the maximal worst pay of this here, the result of our differential game against nature. Now, we apply Dynkin's formula for a function nu, right? And we get this part here. Now, the inequality holds because J is supposed to be supremum. Now, by the so-called exponential ergodicity I just mentioned, we can dominate this expectation by this expression right here. So you can just see why we're talking about an exponential ergodicity, because if t grows too much, then this thing just goes to zero. And that's precisely the case, because when we let t go to infinity, then we get this inequality. Now, we can proceed analogously to obtain the reverse inequality, right? With that, we can get that the verification result is proved. Now, what this result proves is that our insights on the numeric example are correct, because what we just said was that in the bad state of the light, of the traffic light, the producer can consume up to eta, and in the good state, he should just consume up to gamma. Now, I need to ask you, are there any questions so far? No? Okay, good. Okay. This next example is technically a minor modification of the former. However, I believe it to be of big importance due to its applicability. So, I'm talking about an inventory system, see? And I'll focus on these two parts. Here, we consider a single parallel machine system studied, for instance, in Seti's book. And well, please observe that this switching diffusion is essentially the same as before, with the little change that here we are not multiplying alpha by x. We just let it alone. However, our simulated trajectories reflect that that little change might not be that small at all. You see? Now, I need to tell you what each of these parts represent. So, X is the stock level of an inventory. Alpha is a demand rate. U is a production rate, right? And theta should be a machine capacity. However, you all must note that here there is no explicit dependence on such theta. I'll show it a little bit later. Now, we use the same sort of performance index, but here it does not represent a utility, but a cost for a surplus, for having a surplus in the inventory, and for having a producing level. Now, we have here what I like to believe is a very restrictive assumption, because what this says is that the worst thing that nature can do is actually lower than the installed capacity of the system. So it's important to note that the states of the single finite chain are given by the possible inventory levels, and that this assumption says that nature never demands more than the installed capacity of the system. However, we assume that we work with distributions, that is, with relaxed controllers or mixed or randomized strategies. That's why this assumption might not be that restrictive at all. Now, we apply a modified version of theorem 2.1, right? And to find the strategies for the controller. And again, it turns out that the optimal strategy is to produce as much as possible in each state. So we see here, I just showed you the pseudocode for the Ito integral, and I just showed you the pseudocode of the Monte Carlos algorithm. But in here, I show you actual code in a very simple programming language, which is Visual Basic for applications. And here, I just show you how it looks in a spreadsheet. So for a high demand, for a random demand, and for a low demand. And here you see that since we're talking about costs, then this is definitely the worst case scenario. So should the controller be interested in controlling this inventory system, then he should be ready to pay as much as this amount. Now, we're working with a class of control diffusion processes with infinite horizon, whose dynamics has the form of Nito diffusion, along with a transition rule for a certain continuous time Markov chain, where the drift coefficient depends on an unknown and possibly non-observable parameter. Now, due to the lack of knowledge of such parameter, we reformulate the problem as an optimal control model under ambiguity, or game against the nature. These models can be applied in vaccine distribution, allocation of renewable resources, or measuring the effectiveness of molecular programs. Now, in these two first models, the rate of infections or rate of births and deaths depend on the density of random variable, and the objective is to reduce the spreading of a disease here, or to maximize a consumption functional here. While in this problem, the utility of the robust approach lies in the comparison of the main program with other competing programs. Our work can be located in the field of optimal control models with Markovian switching under the average pay of Criterion. Now, we impose some general conditions on these sets, which are supposed to be compact, right? And on the kind of continuity that the drift and diffusion coefficients satisfy, and the possibility of considering an unbounded reward function. Now, observe that in these two cases, for the coefficients B, gamma, and R, we assume that this special kind of continuity is just Lipschitz continuity. Here are the references. And well, I thank you all very much for your kind attention.
Okay, thank you, Daniel, for the presentation.
Thank you.
Thank you. So, dear colleagues, please.
By the way, let me just ask, the links to these papers or the papers themselves will be posted on the website of the workshop at Stony Brook if the authors are going to provide it.
I'll be honored.
Huh?
I'd be honored if such.
I I think
Thing happens.
I'm suggesting we did this for our international conference last week. I suggest for the workshop also, those authors who have papers that they want to post, they could send it to us and we will put them on our website so that people can look at it later.
Thank you very much.
Thank you very much. Yes, that would be great. Yeah.
Thank you, Professor.
Do you have any questions about the presentation? Daniel, in your example, you demonstrate the dynamic which does not depends explicitly on theta. Yes?
Yeah.
So, could you explain again?
Of course. So,
yes, here.
Here there is no explicit dependence on theta. However, just as in the previous example, what we assume is that this demand rate is lower than the states, right? And thus the result is that for this some sort of pendulum, right? Because for the numerics here, I just assumed that there were two states. What I assumed was that we could just go from 1 to 2. In this simulation, this is an unfortunate simulation because it shows only once, but actually in the program this goes from 1 to 2. But the thing is that in all these numbers here, right, the demand is always bounded by this number, bounded below by this number.
Is it realistic that the demand is bounded by some value in the economical applications?
No, in the economical application, it's not. However, I was telling you that I actually cheated because when I showed you this sketch of the proof, I didn't actually use relaxed controllers. The relaxed controllers are supposed to be probability distributions. But if we use that assumption and if we use randomized controllers, then what we'll have in here will be numbers that are actually lower than 1. So our assumption will not look as restrictive at all.
Okay, and at the beginning you said about the technique of vanishing discount, yeah?
Yeah.
What's this?
Okay. This okay. So what we do is that we use dynamic programming to solve a discounted problem, a problem on infinite horizon under the discounted criterion. And then we use this vanishing discount technique by means of a bias function. This H right here is a bias function. And then we just set suitable assumptions in the paper. I dub them as assumptions 1 and 2, right? So that these conditions 20, 29, and 30 hold. So that's very briefly what the vanishing discount technique is.
But it's difficult for me. So it was published in your paper, yes?
Yes, it's in the paper, yeah. Actually, this is precisely the link to which this paper right here is a link to the draft I sent with my colleagues to Acta Matematica Applicante.
Mm-hmm.
Yeah.
Okay, thank you.